Morning, everyone. How are we doing? Questions while we wait? Morning, everyone. We have time for one more. Still thinking about the favorite current favorite artist. What does that mean? What do we current as in who's my favorite artist now, or the current artist?
asking what I've been missing. I tell you truthfully, she's coming close down. I can feel her. She's getting close to me.
All right, morning everyone. Not familiar with Cooler Shaker there. Have to look that up. Also, favorite. I don't know. It's always difficult. I mean, I'm a big fan of the hip, but also a big fan of Pink Floyd. I've been listening to a lot of rap recently. I don't know. It's all good. All right, let's move on. Questions? Any questions before we begin? Anybody? We're going to discuss. Midterm has been graded. We're just finishing up those that had technical difficulties. So maybe this afternoon or tomorrow we'll release the grades. We're not doing differentials. Midterm average, I just looked that up. I thought it was higher. Seems a bit low, 55. We'll see. Yeah. All right. I mean, no need to worry about that now. You know that we have announced an alternative grading scheme for those who may not have done well on the midterm. If you did not do well on the midterm, use it as a wake-up call that more work needs to be done. And as you know, for the final exam, assuming it's going to be in person, which I firmly believe it will, I just wrote the final exam over the weekend. All the questions are taken from the odd-numbered exercises in the book. Final has a very high weight. Indeed, it does, but between 70% and 85%, I mean, there's almost no difference, right? Gabrielle was asking questions 7 and 9. I assume linear approximation accurate to within a certain amount, like question 7 and 9. I don't have that question 7 and 9 here. Either give it to me, or yeah, I think if you can give it to us, that would be better. Well, I mean, let's say this: the final is going to be more straightforward, right? I mean, here, since the midterm was online and you could use everything that the internet has to offer, essentially, then it had to be questions that were not easily answerable using those things. So it's going to be odd numbered questions from the book. Thank you. Yeah, we did not do that, and the reason I'm still answering Gabrielle's question here. We didn't do that, and the reason we did not was that there's a nice way to answer those questions when we get to Cal 2. So don't worry about those kinds of questions. They are just odd numbered, taken directly from the book. Yeah. Final is cumulative. So as long as you do the odd numbered questions in the book, you should be fine. You should be fine. Well, I mean, I don't mean do them by reading the question, then looking at the answers in the solutions manual, right? You know that's not what I mean. If you can answer the questions, the odd numbered exercises in the book, without resorting to the solutions manual, you will do very well. Yes, thank you. So those linear approximation questions where they're asking you how accurate. We did not cover that, so that you're not responsible for that. Orthogonal trajectories, those are nice questions. We did not define what an orthogonal trajectory was, but they do define it in one of the odd numbered exercises. So it is fair game. I have not put any proofs on the final. Well, I mean, no. Yeah. Well, actually, let me take that back. It depends what you mean by a proof. 55%, Eddie, was the average. So it really depends what you mean by proof. As far as I'm concerned, there are no proofs on the final, but some people might interpret something else as a proof, whereas I do not. All right, let's move on. As far as I'm concerned, there are no proofs on the final. But again, well, I mean, look, let's move on to the new material, and I'll show you an example of a question that could have been on. The final is at the same time for everybody. So today we're going to do hyperbolic functions. most people don't put the word trig there. They're just called hyperbolic functions. And well, that's the thing. That's exactly it. Some people could interpret show as prove. So, yeah. So hyperbolic trig functions definition. So let me define hyperbolic sine. Right, this is not sine of hx, but rather hyperbolic sine of x. This is defined to be e to the x minus e to the minus x over 2. Similarly, hyperbolic cosine of x is defined to be e to the x plus e to the minus x over 2. Once hyperbolic sine and cosine have been defined, we will define the 4 remaining hyperbolic trig functions, namely hyperbolic tangent as hyperbolic sine over hyperbolic cosine. So this over that. The 2's cancel out nicely, and we get e to the x minus e to the minus x over e to the x plus e to the minus x. And so on, right? Hyperbolic secant is 1 over hyperbolic cosine. So that is 2 over e to the x plus e to the minus x. Hyperbolic cotangent is hyperbolic cosine over hyperbolic sine, which is e to the x plus e to the minus x over e to the x minus e to the minus x. And finally, hyperbolic cosecant, or 1 over hyperbolic sine. That's going to be 2 over e to the x minus e to the minus x. Right? I mean, many questions arise. Why are they called hyperbolic? Why are we using sines and cosines? Where do these come up? Lots and lots of excellent questions. Let's answer these. In the past, I didn't really cover these hyperbolic trig functions. Because as far as I'm concerned, there's nothing happening, right? It's just a combination of exponentials. And you're very comfortable with exponentials, so there's really nothing happening here. But then I figured this was a disservice to students, because first of all, they're very easy, right? Again, they're just a combination of exponential functions. So there's nothing to be worried about. Nothing difficult is happening here. Secondly, they arise naturally. And here's how they arise. If you have 2 poles, think of telephone poles, and you run a wire from one pole to the other. Under the pull of gravity, this will naturally take on a hyperbolic cosine graph. This can be done by solving the differential equation that describes how the wire settles. So run a string, run a wire, whatever, it's going to naturally take on the hyperbolic cosine graph. So it's best to introduce them here and play around and learn them here and play around with these than to do so in another course where not only is it assumed that you know, but no, that's the thing, right? I mean, again, it's not tangent of hx, but rather hyperbolic tangent of x. So this is this is the h from hyperbolic. It's hyperbolic sine, hyperbolic cosine, and so on and so on. Well, I mean, it's indeed it's going to depend on the length and this and that, but well, I mean, the real solution, I think, is a plus hyperbolic cosine of x over a, or anyways, something of that form, where a is going to depend on the length and maybe the material and so on and so on. All right, so that's why we're discussing them, because they arise naturally in solving some differential equations. Well, so if you're still confused, what am I doing? I have defined hyperbolic sine. It's like a new function, right? It's a new function. I'm defining a new function. Hyperbolic sine of x, this is it. Hyperbolic cosine of x, this is it. And now we'll define 4 others. Tangent, hyperbolic secant, hyperbolic cotangent, hyperbolic cosecant, in essentially the same way that we do with the sine and cosine. Right? So why the name? Well, the properties are similar to the sine and cosine. So the properties are similar to sine and cosine, as we will see in a moment. Not so much. Pratik is asking if we can define them in terms of hypotenuse. Well, not so much. Well, short answer, yes. Long answer, no. What do I want to say about that? What do I want to say? The question arises naturally, why use the sine and cosine for these? How did we know? And what's going on there? Doesn't the curve drawn look like y equals x squared? Kind of does, but it really follows this. What do I want to say? So to answer y sine and cos, or y hyperbolic sine and y hyperbolic cos, if you're interested, I mean, maybe we can skip it if you're not. But to answer y, we have to move to the complex plane. And if we define I to be the square root of negative 1, there's a beautiful result known as Euler's formula, which says that e to the I theta is sine theta plus I cosine theta. And consequently, e to the minus I theta, which can be thought of as e to the I negative theta, right, is going to be sine of negative theta plus I cosine of negative theta. But sine of negative theta is negative sine theta, and cosine of negative theta is the same as cosine theta. So if you add these two together, you see that the sines disappear, and you're left with just two of these. So cosine of theta is e to the I theta plus e to the minus I theta over 2i. And if you forget the i's for a moment, you have exactly this business. And similarly, if you subtract this, minus minus becomes a plus, these disappear, and you get e to the I theta minus e to the minus I theta is 2 sine theta, thereby giving you this idea. I'm just saying, I'm giving justification. I mean, this is way beyond us here. Euler's formula is way, way, way beyond us. But that's the reason behind calling it hyperbolic sine and cos. Well, I mean, really the question was why hyperbolic? And the reason is that these functions are known as hyperbolic functions. The e to the I theta business. Let's discuss. Rachel's asking how I got 2i cos theta. I added these. So this plus this, right? These add together. This plus this, these cancel out, and you have 2 of these. Claim hyperbolic sine of negative x is negative hyperbolic sine of x. Let's prove it. Right, so here's a question from the final, right? If I asked you to show that hyperbolic sine of negative x is negative hyperbolic sine of x, is that a proof? In the question, this is, I mean, in the book they have a bunch of these as exercises. I would not consider these proofs, but perhaps you would. But again, there are many of these in the odd-numbered exercises, so they are fair game. Now, I said I don't call them proofs, and yet I write proof there. So, yeah. So let's start with what we know. We know hyperbolic sine of x is e to the x minus e to the minus x over 2. So hyperbolic sine of negative x, just replace x with negative x everywhere. This is e to the negative x minus e to the negative x over 2. And this is e to the negative x minus e to the x over 2. And if I factor out a negative, this becomes e to the x minus e to the negative x over 2, which is negative hyperbolic sine of x. Very simple, right? Let's consider another claim. Hyperbolic cosine of negative x is the same as hyperbolic cosine of x. Right? H sine would have made more sense. Absolutely. But then people might have thought, well, is h a variable? I did not factor out a minus 1 from the exponent. I factored out a minus 1 from the numerator. Factor out a minus 1. So minus outside, minus here, and plus there. And you're right there. Let's prove this. And really, it's just playing around with the definition of hyperbolic trig functions, right? Hyperbolic cosine, we have the definition up there. Hyperbolic cosine is e to the x plus e to the minus x over 2. There's really nothing going on here, right? We're just playing around with the definition. The definition is new to you, so you have to learn it, but we're learning it through proven other things. Hyperbolic cosine of x is this. So hyperbolic cosine of negative x, just plug in negative x instead of x. And this is e to the minus x plus e to the x over 2, which is the same as e to the x plus e to the minus x over 2, which is exactly hyperbolic cosine of x. So hyperbolic cosine of negative x is equal to hyperbolic cosine of x. And here we show that hyperbolic sine of negative x was negative hyperbolic sine of x. Let's take a moment to introduce a definition that the book introduced a long time ago. We probably should have done so as well, but we never really needed it. But it's going to become important very soon. Definition: a function f of x is said to be even if f of negative x is negative f of x. No, so it is. F of negative x is equal to f of x. A function g of x is said to be odd if g of negative x is negative g of x. Pratik is asking what we mean by even. This is the definition of even. f of negative x is the same as f of x. So not even y values. But let's think about what this means from a geometric perspective. If you take a value of x and you look at its negative, f of x and f of negative x are equal. So they have the same y value. In other words, there's symmetry about the y-axis. And as Kahn suggests, we have just shown here that hyperbolic cosine of x is even. Absolutely. Right? So what does it mean for a function to be even? It means that there will be symmetry about the y-axis. What about when a function is odd? Melanie's asking if we will be doing curve sketching. This is really where the course is leading us. Not next week, but later this week, we're going to ask the question, what does the derivative imply about the original function? And we're going to see these nice properties, and we're going to use everything to ultimately graph as best we can. And Bree is suggesting that we have shown, right? I mean, in the example we raised here, we show that hyperbolic sine of negative x was negative hyperbolic sine of x. In other words, hyperbolic sine of x is odd. Absolutely. And what does geometrically, what does being odd mean? It means that g of negative x is negative g of x. So whatever happens at g of x, its negative will happen over there. So there's really symmetry about the line y equals negative x. I don't like to think of it that way. I like to think about it as reflection about the x-axis and then about the y. But that's just me. It really means symmetry about the line y equals negative x. Questions? So, right, I mean, hyperbolic cosine is even, hyperbolic sine is odd. Paul's asking an excellent question. Can a function be neither odd nor even? Before we answer that, let's look at a few other odd and even functions. Right? Let's look at the cosine function. You know the graph of cosine. And what do you notice? You notice symmetry about the y-axis. Cosine is even. Cosine of negative x is cosine of x. You can prove that using properties of sine and cosine, but from the graph, there you have it. Cosine is an even function. Similarly, sine of x is odd. Let's take another example. 2x cubed minus x is odd. Let's prove it. And Sophia's suggesting x squared is even. Absolutely. You can prove it. And 2x cubed minus x is odd, right? The odd and even names coming from the powers, right? As Sophia suggests, powers of x which are even are going to be even functions. Powers of x which are odd are going to be odd functions. Let's prove that this is odd. What do we have to prove? If you plug in negative x, this should be negative f of x. But what is that? This is negative. So everywhere you see an x, replace with negative x. So this is 2 times negative x all cubed minus negative x. Negative x all cubed is negative x times negative x times negative x. So you have 3 negatives there. So this is 2 times negative of the x cubed, right? Negative x times negative x times negative x. So 3 negatives gives you negative. And x times x times x is x cubed. So in other words, minus 2x cubed plus x. And if you factor out a negative, it's 2x cubed minus x. And this is your original function. So that function is odd. Let's prove Sophia's claim. Sophia suggested that x squared is even. Let's prove it. First of all, you know the graph, right? You know the graph. You know that there's symmetry about the y-axis. So that's why it's even. But let's prove it from the definition, right? Because we don't want to use the graph to deduce anything. Rather, we want to do the opposite. So are all functions with even degrees even? Let's be careful with that. Yes or no, it depends what is meant. We'll take an example in a moment. So let's prove that this is even by plugging in negative x. So this is negative x all squared, which is negative x times negative x. Negative negative is positive, and you've got x squared there, which is your original function. So perhaps Sophia is asking, if you have a polynomials with only even powers, then yes, the answer is that this will be an even function. But Paul was asking, can a function be neither even nor odd? And the answer is yes. A simple example is x plus 1, say. What is f of 1? F of 1 is easily seen to be 2. F of negative 1 is easily seen to be 0. So f of 1 is not equal to f of negative 1. So f is not even. And f of 1, or f of negative 1, is not equal to negative f of 1. So f is not odd. Right? So this function is neither odd nor even. Right? Really, any function that is not symmetric above the y-axis or about the x and then the y, or the y and then the x. Right? So this idea of being odd or even is very, I wouldn't call it rare, but it's a special condition. Let's consider another. So even functions are symmetric above the y-axis, correct? Even functions are symmetric above the y-axis. Odd functions symmetric above the x and then the y. Or equivalently about the line y equals negative x. That's a bit harder to see, but that's what's happening. Claim, right? Again, hyperbolic trig functions versus the regular trig functions, right? They have, well, first of all, the property that hyperbolic cosine is even, very much like the regular cosine. Hyperbolic sine is odd, very much like the regular sine. Some properties are exactly the same, others are similar, but not identical. Case in point, you know that sine squared plus cosine squared equals 1. We have a similar identity involving hyperbolic trig functions, not identical, but similar. Hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. If e to the x is not odd or even, and you know it isn't, right? Because you know the graph of that. There's no symmetry above the y-axis. And if you flip it this way, of course you don't get that business. Correct? If hyperbolic trig functions are made up of exponentials, how are they either odd or even, right? So it's a good question, but we proved it. We proved it. So even though it's made up of two pieces that are not odd nor even, it turns out that the sum was still even. Very nice observation. And Kripa is asking, is the inverse of an even function always even? First of all, we have a big issue with even functions, right? Even functions have this property. So if x is not 0, then the function is not 1-to-1. Right? So Eddie's asking the quick question, can an even function even have an inverse? Right? If you have symmetry about the y-axis, this function will not be 1-to-1. Exactly that. Right? So even functions are not 1-to-1, and we're in trouble. Let's prove this property that hyperbolic cosine squared minus hyperbolic sine squared is equal to 1, right? Similar to its trig equivalent, but not identical. You know that hyperbolic sine of x is e to the x minus e to the minus x over 2. And hyperbolic cosine of x is the same thing, but with a plus. So let's square these. And subtract them. So it's this squared minus this squared and FOIL this business, e to the 2x. This times this, the exponents add to give you e to the 0, which is 1. Right? So this times 2 just gives you 2. Does everybody see that? Plus e to the minus 2x all over 4. Minus, similarly, this squared, which is e to the 2x. This times this gives you negative 1, right? E to the, well, negative e to the 0 times 2 plus this squared, e to the negative 2x over 4. Everybody with us? Open that up. These cancel out. These cancel out. And you get 2 over 4 minus negative. So plus 2 over 4. And as, who was it? Pratik suggested, 4 over 4, which is 1. Not a difference of square, well, where did the 2 come from? Just expand this, right? Square it. So FOIL that, or this square, this times 2. But this times this, the exponents add to give you e to the 0. So it's 2 times e to the 0, which is just 2. People, do we have the 2? Everybody comfortable with the 2? Stop me now. We good? Moving on. Thank you. So there it is. There it is. Hyperbolic cosine squared minus hyperbolic sine squared equals 1. But now, if you remember, for this one, we had 2 for free by multiplying by 1 over sine squared, or by 1 over cosine squared. Right? If you multiply by 1 over sine squared, you get 1 plus cotangent squared equals cosecant squared. And if you multiply by 1 over cosine squared instead, you get tangent squared plus 1 equals secant squared. Colin, that's incorrect. A plus B, that's a squared plus 2ab plus b squared. You're missing the 2ab business. So this should be 2 e to the x, e to the minus x, and the exponents add to give you 2 e to the 0, which is 2. So now that we've established this identity, we get 2 for free by multiplying by 1 over hyperbolic cosine squared to get 1 minus hyperbolic tangent squared is equal to hyperbolic secant squared. Right? So similar but different. Right? Here we have tangent squared plus 1. Here you have 1 minus hyperbolic tangent squared. And similarly, if you multiply by 1 over hyperbolic sine squared instead, you're going to get hyperbolic cosine over hyperbolic sine, or hyperbolic cotangent squared minus 1 is hyperbolic cosecant squared. Be careful, Rachel, right? There's a negative in there. It's not the exact same thing. Here you have cotangent squared plus 1. Here you have hyperbolic cotangent squared minus 1. All right. Now, as I suggested, the book has lots and lots of these properties or identities to show. I'll let you show them. I'm sure you're asking yourself the following question: what about the derivatives? Right? You know that the derivative of sine is cos, and you know that the derivative of cos is negative sine. What about the derivative of the hyperbolic trig functions? Let's work it out. It'll only take a minute. Hyperbolic sine. Exactly, right? As Kant suggests, let's rewrite these in terms of exponential functions. Because now, if we rewrite them in terms of exponential functions, you know the derivatives of these things. So this is very easy. Finish it up, right? The 1/2 is just a constant, so let's take that out. Derivative of e to the x. Exactly as Kant suggests, we all know the derivatives of e to the x. You don't need to use the quotient rule, Zuhair, right? You can pull out the constant. But there's nothing wrong with doing the quotient rule anyways. You'll get the same answer. It's just going to be a bit longer. I'll let you do that as an exercise. Derivative of e to the negative x is e to the negative x times the derivative of the inside. Derivative of negative x is -1. So what do we get? 1/2 e to the x plus e to the minus x, or e to the x plus e to the minus x over 2, which is easily seen to be hyperbolic cosine. The derivative of hyperbolic sine is hyperbolic cosine. What about the derivative of hyperbolic cosine? What is the derivative of hyperbolic cosine? Well, again, hyperbolic cosine is e to the x plus e to the minus x over 2. The 1/2 is just a constant. Let's take that out. Derivative of e to the x is e to the x. Derivative of e to the negative x is e to the negative x times the derivative of the inside. And as Rachel suggests, well, Rachel suggested negative hyperbolic sine, right? Because you're thinking to yourself, the derivative of cosine is negative sine. But here, we see that the derivative of hyperbolic cosine is just hyperbolic sine. It's all the same, Con, right? There's no negative here. There's no negative. You might have expected a negative, but there isn't. It's similar, but not exactly the same. Now that we've worked out the derivative of hyperbolic sine and hyperbolic cosine, I'll let you, for fun, work out the 4 remaining ones. We'll do them on Wednesday. But go ahead and do them. It's good practice. And you know, I don't even know them by heart. And I don't need to, because I can always take 10 seconds, 15 seconds to work it out. There's nothing happening here. It's just exponential functions. When you're doing the derivative of hyperbolic tangent, rewrite it as hyperbolic sine over hyperbolic cosine and do the derivatives using the quotient rule. You'll find exercise on page 267. The section is called hyperbolic functions. So practice this. We'll pick this up again on Wednesday. No differentials. I don't want to release some of them without releasing all of them, because you know what's going to happen. I'll be swamped with emails saying I did not get my grade, blah blah blah. I don't want to have to deal with that. So we'll release all of them simultaneously. So as soon as those last ones are done, we'll release everything. Thank you all for coming, folks. We'll pick this up again on Wednesday. I think I released a web work last week, right? Have a look at that. All right. You guys have a good one. See you then.